Morning, everybody. Excuse me. My throat is a bit hoarse, so I will try to talk a bit slower today and a bit softer, but to compensate, I will raise my mic volume and try to let the mic do the work. Okay, how's that? All right, so as I posted about on Piazza, one option for today's lecture is to do what I originally planned for lecture, which is a case study on legislator ages. The point of the case study is to essentially go through some of the key ideas introduced thus far in the class in an applied way on some real data. I'm also open to reviewing some topics with you if you'd like to do that instead. And so what I've done here is I've created a topic review form, which you can access either by going on the slides or by looking in your email for that Piazza post that I sent out this morning. And I think without looking at the responses, looking at this room, it looks like if I get more than 20 responses on this form, then I will go through some topics. But if I don't get more than 20, then I will just go through my case study. So I will pre-commit to some decision here. So if you'd like to fill it out, or if you want me to go over some topics, go ahead and fill out that form. Otherwise, I'm going to assume that you want to go through the case study. Okay, so if you want to fill out the form, do it now. As a reminder, homework 3 is due tomorrow night, so do make sure you have that in. Again, you want to make sure you have both Gradescope. You want to make sure you have both Occupy and Gradescope turned in before 11:59 p.m. tomorrow night. Midterm is happening next Tuesday, which is in 5 days from today. It will take place here in this lecture room. You are allowed to bring a single handwritten 2-sided cheat sheet on a letter-sized piece of paper. Don't come in bringing a poster board. And we will provide for you a reference sheet for Pandas, regex, and SQL. We posted a link on Piazza, and if you want to take a look at it now, if you haven't seen it yet, I'll just pull it up now so you can kind of take a look at it. Let's see here. Let's open that. And so it looks like this. We'll hand out a copy of this to everybody who's coming in to take the exam, so you don't have to write any of this on your cheat sheet if you don't want to. Okay, so we have here like some loc syntax, fill in A, how to drop, how to call merge, how to set index, reset index, some basic operations on grouping. We have here some string operations, plotting operations, regular expressions, SQL. And so this is just designed to help you not treat the test as a memorization test, because it's definitely not designed to be a memorization test. What you're trying to do instead is focus your time on learning how to apply these tools and how to use them. Okay, let's go back here. We have a midterm review session on Monday in place of lecture, so we're going to be going over some practice problems for the midterm. Okay, so for midterm 1, we're going to be going over study design, Pandas, visualization, strings, SQL, and PCA. It's an 80-minute exam, which is not that long, so I can't grill you on the super fine-grained details of every one of these topics, but I will try to touch each of the topics at least once on the exam. So you should be familiar with them, and don't expect to have to do some crazy matrix multiplication thing. I won't go beyond what I talked about in lecture when it comes to these topics. So for example, on PCA, I did not talk about eigenvectors or eigenvalues or what those mean or what those are. So you won't have to know those things for the exam, but you will have to know, you will be expected to know something like what are the vectors in U represent, what do the values in S represent, because we talked about those yesterday. All right, let's take a look at the form. How many responses? We got 25 responses. Okay, so it looks like we're doing some topic review. it looks like a lot of people wanted to look at PCA, a lot of people want to look at text, and some fewer people want to look at SQL and data cleaning. Okay, so people are confused about PCA. Let's take a look here. Second choice of topic, SQL, PCA, text, cleaning. Okay, so kind of the same thing here. More SQL, some visualization. Okay, so it looks like everyone really likes PCA. Yes, I'll use the word like. PCA is in demand, let's say. Let's see. Next, I think it looks like text is probably coming in second. And then we have a chunk of people that want SQL and some people who want visualization. Okay. What's the best way to do this? How about you talk with your neighbor about some topic from PCA that you'd like me to go over? And what I'll do is you can go back to my slides here, and you can pull up the slides for PCA or dimensionality reduction, or I guess you would go to the website. So you can go ahead and go through PCA, dimensionality reduction, pick a few slides you want me to go over. So just say okay, on lecture 10, slides number 15, can you go over slides 15 through 19 again? And I can do that for you guys. Okay, I'll also try to provide you some ideas for exam questions I could write. Okay, so I'll try to walk you through my thought process of writing exams. Again, it's not when I give the exam, it's not to grill you. I will make it challenging to try to measure, try to get a sense of what you've learned, but I'm not trying to destroy your hopes and dreams for becoming a data scientist through the exam. So I will try to explain to you my thought process for designing questions, and hopefully that'll give you a better idea for what to expect for the exam come Tuesday. Okay, so let's start with PCA, and then we'll spend I'll just we'll talk about PCA with your neighbor, and then I'll just try to go around and somehow collect some indicator of what topics you guys would like to go over. And then if time allows, we'll do the same for EDA and text, as well as visualization and SQL. Okay, so go ahead and do that, and I will figure something out in the meantime. Go ahead. All right. So we had 2 lectures on PCA. We had lecture 10 and lecture 11. And all right, so I guess maybe the most feasible way for me to do this is to ask for some volunteers to raise their hands, and I'll just try to get as many hands as possible, and I'll just try to cover as many hands as possible with the slides that I pick. Okay, so if you don't speak up, basically if you don't speak up now, you might never get your topic reviewed. So you should speak up if you want, if you feel confused and want to go over some slides. Okay, so anyone have suggestions for slides to go over for PCA, either lecture 10 or lecture 11? Okay, I see no suggestions. Yes, Emily. Lecture 10, slides 9. Are there more slides, or is it just that one slide? Okay, so let's take a look here. I have here dimensionality reduction, slides 9 through 11. Okay, so kind of the intuition for linear algebra, matrix multiplication. Okay, any other suggestions? Yeah, Sophie?
From lecture 11, just the interpretation of
The interpretation, okay, so interpretation of U, V, and sigma. Okay. And by interpretation, you mean how do we interpret the values or columns inside each matrix? Okay, yep. Yes, Julie? Okay, so, lecture 9, not bad. Wait a second. You know what? I think we're both right. So I think what happened is I have a number on the syllabus for July 4th, but it doesn't count as an actual lecture number. So let's say I think it's lecture 9 and this is lecture 10. Okay, so what was the question again? 26 to 29. Okay, so details of SVD. And by details, do you mean what SVD is doing, or just a recap of?
Like the scale, for example, U is V of the inclusion matrix.
Oh, okay. So
Later on we talk about how SVD is equal to sigma, U sigma. And then they're trying to connect those two.
Okay, yeah. So the connection between the UV sigma of SVD and what we're doing in PCA, or how we interpret those in PCA. Okay, yeah, that's good. I like that. Okay, any other suggestions? Yeah, Tiff? Okay, so I see here 9, 12, 15 through 19. I'm basically going to go over my entire PCA lectures, like both of them. Oh no, it's all good. Okay, so I see here on 9 we have the connection or the vocabulary we use for SVD and PCA. I see here the procedure to compute PCA. So 15 through 19, I see here the variance, the interpretation of variance, scree plots, and the goals of PCA in a declarative way. Okay, so basically all of PCA. Okay, so that's fine. Fine by me. I'll do that. So let's see here. So I think I already have connection between SVD and PCA. let me write down here the recipe, PCA. I'm going to write down here the variance interpretation of PCA and interpretation of first principle component. Okay. It's a lot of stuff. Okay, any other suggestions? Okay, so let me see if I can give you a, all right, unfull screen this. Let me pull up lecture 9. Take that, okay. All right, let me look over here. I'm gonna try to like whip together a mini lecture in like 2 minutes. So give me like 2 minutes. Let's take a look. Okay. Someone's like timing me. Okay, so I'll go over the slides in roughly the order, but what I'll do here is when we talk about SVD, I will skip ahead to PCA and try to like give you that integrated view of like the UV sigma across SVD and PCA. And then after we do that, okay, so I'm going to do this, move this first, and then go over the how to do PCA, and then go over the interpretations. Okay, so I think that sounds pretty reasonable to me. Let's do it. Okay, so we talked in homework 1 about how to like encode some calculations using matrices. And so when I'm calculating the cost of fruit bowls, I could do it by hand, right? So I could say something like, okay, if fruit bowl 1 is 2 of each fruit, then I could pretty much take like my hand calculator and calculate myself like, okay, 2 times the apple price, 2 times the banana price, 2 times the melon price, and that will give me the cost of fruit bowl 1. I can do the same here for fruit bowl 2, but it's going to get very complicated and unpleasant if I have 100 fruit bowls. Right? So if I have 100 fruit bowls and like 100 stores, then doing like every single like addition multiplication thing by hand becomes a big pain. And so one way to like succinctly describe some linear calculations is via a matrix multiplication. Okay, so in this case, what I've done here is I've kind of used the mechanics of matrix multiplication to encode calculations. Okay, so the calculation on the left here encodes like the fruits in each fruit bowl. The prices on the right here, or the vector on the right here, encodes the price per fruit. Okay, so you can follow with me the units of this matrix, right? So I have here fruits in each fruit bowl, and then I have here dollars for each fruit, right? Fruit in each fruit bowl, dollars for each fruit, and I'm also describing to you the columns and the rows, like what the columns and the rows represent for the matrix. So in this first matrix here, the columns represent the fruits, and the rows represent the bowls. In this matrix here, the column represents the dollars, or the cost, and the rows represent the fruit. Okay, and so you may notice here that the rows units of this right vector here are the same as the column units of this matrix here. And so that's why we can get the interpretation that doing a matrix multiplication is doing a linear operation on some data. Because this right here, this calculation right here, is essentially a shorthand or another way to write like 2 times 2 plus 2 times 1 plus 4 times 2. It's just shorter. And so that's why we like to do, that's why we like to put it in matrix form. Okay. Okay, and so the way, or the more common way that we'll look at matrix multiplication in this class is we'll say that one matrix is our data and another matrix is our computation. Okay, so in this case, I've assigned, this is not like something that's built into matrix multiplication. is something that I'm just doing so I can try to make sense of it for myself. Okay, it's like a personal personal aid for myself to make sense of what's going on here. When you're learning about matrix multiplication in like a math class, they'll just give you like a box of numbers most of the time, unless the instructor is pretty good. Okay, and so what I'm doing personally is I'm saying one matrix is the data and one matrix is a computation, and that helps me to interpret what's going on here. So I'm saying I'm going to apply some functions or some operations to my data. Okay, so similar to how like I can take the mean or like the max of a column in Pandas, I can do like some linear combination of the data by using a matrix multiplication. Okay. Let's see here. The way you develop intuition for this is to try to like mess around with some matrices yourself. So if you want to develop some more intuition for these linear operations, then what you can do is you can take, let's see. You can try to come up with some real world examples yourself. So for example, you can do something like every row is a person in the class, and every person here has like 2 t-shirts, and you can have like t-shirt prices here, for example, and you can like do the matrix multiplication like that. There are probably other examples. If you look in your like math textbook, if you look at the word problems, which I like hated, you can actually use the word problems as like some inspiration to make your own matrices and try to get some intuition that way. Okay. Let's see here. Okay, and then one important thing to know is that because it's just me personally assigning like data and computation to one matrix or the other, I can also flip which matrix I assign, like I treat as data. And so sometimes what you'll see me do is you'll see me treat the left matrix as data and the right matrix as a computation. Other times you'll see me do the right matrix as data and the left matrix as computation. I'll just try to be clear, especially for today, like which matrix I'm treating as what. Okay, but basically, you can do either one. Like most problems make sense if you flip the computation and data like assignments. You just have to interpret the results differently. Okay, so in particular, that's what we're doing when we say x times v is equal to u times sigma. What I'm doing in x times v is equal to u times sigma is I'm saying, for example, that x is the data and v is the operation. Okay, when I say u times sigma, I'm saying u is the data and sigma is the operation. But when I talk about x equals u times sigma times v transpose, I'm usually treating v transpose as a data and u and sigma as the operations. Okay, so I'll go over those in some more detail today. But basically, I just make the assignments so that I can come up with the best interpretation for me. Okay. Let's see, what else do I have? Okay, so details of singular value decomposition. Okay. Okay, so for example, I'll give you like one example exam question. I could very easily ask you these questions here, but using a different set of data here. Okay, so for example, I could say every row is a person with t-shirt sizes. Every column here is like a store that sells t-shirts. Like what store should Sam go to get the best price for what he wants to buy? That's a very easy question. Like I could also ask, if I add a new row, what does that represent? And give you like a multiple choice question that says like this, adding a new row here represents adding a new store, or adding a new t-shirt size, or adding a new person, and that sort of thing you should be able to interpret. Okay. Let's talk about singular value decomposition. Okay, so to interpret SVD, what you should remember is that orthonormal matrices. Okay, so if we have an orthonormal matrix, what I'll usually do is treat that orthonormal matrix as a rotation. What I mean by rotation is here, what I've done is I've said this matrix right here computes the price for each fruit bowl. Okay, so it does like some computation. For orthonormal matrix, I will say that the matrix doesn't compute some price, it instead rotates some vectors around. Okay, so right here I have v1 and v2, and right here I have v1 and v2, I just don't have them labeled here. but I can represent those vectors as data. Okay, so I can write, so this vector right here has x coordinate 1 and y coordinate 0. This vector up top here has x coordinate 0 and y coordinate 1. I can put those vectors into a matrix, right? In this case, it would be a 2 by 2 matrix. Okay, and what I can do is when I can treat each column of that matrix as the dimensions of a vector, and then when I multiply that vector by some orthonormal matrix, what happens, like I can interpret the result of that matrix multiplication as a rotation. And the reason why I can interpret it as a rotation is because every column in Q is a unit vector, which means that it will not stretch the vectors beyond their original lengths. And the columns are orthogonal, which means that it will not bring V2 closer to V1 after multiplication. Okay, so if the columns of Q are not unit vectors, then V1 and V2 will be stretched out or like kind of compressed inward towards the origin. If the columns of Q are not orthogonal to each other, then it's possible that V2 gets moved closer to V1 or further away from V1. But because Q is orthonormal, both the lengths of the vectors are preserved and their distances from each other are preserved, and so I can interpret that operation as a rotation. Yes, Frederick?
How do we determine how much it rotates?
How do you determine how much it rotates? It requires some trigonometry, but I won't ask you to do that, but you can. So if you want to do this in 2 dimensions, essentially the amount of rotation is like, I'm pretty sure something like cosine theta, like sine. You make a 2 by 2 matrix with like cosine theta and like sine theta somewhere in those matrices. Yeah. So if you watch the 3 blue 1 brown videos that I linked in this lecture, then I believe he goes through some examples of that rotation. Okay. So a diagonal matrix only has values on the diagonal, and basically, if I take the same 2 vectors and put their coordinates into a matrix, and then multiply that matrix by sigma here, what will happen is that every vector will get stretched out or like stretched in. Okay, so for example, if the value on the diagonal here was 2, then the first vector on the left matrix will get stretched out by a factor of 2. So in this case, I'm treating the left-hand matrix as data and this sigma matrix as the operation. And what I'm saying here is that the values in sigma determine how far these vectors in my original matrix get stretched out. Okay. And so when I do singular value decomposition, so remember that x here can contain anything. Okay, so there are no restrictions on what is in x. It could have really big numbers. It could have very small numbers. It could have orthogonal columns, or it might not. So it can just contain anything. And what SVD says is I can always decompose my original matrix X into a rotation matrix, a scaling matrix, and another rotation matrix. Okay, so to interpret this, one way to interpret SVD is if I had some vectors, so let's say V1 and V2 are 2 original vectors, okay? And I compute X times the matrix that contains the data for V1 and V2, okay? So what I'll do here is I'll take V1, put its coordinates in a matrix, like take V1 and V2, make a 2 by 2 matrix. Okay, so the first column of that matrix will contain the coordinates for V1. The second column of that matrix will contain the coordinates for V2. And I can compute X times that matrix for the vectors. And when I compute X times the matrix for the vectors, every matrix I can view as some movement or some operation on these vectors. So what will happen is you're going to see when I do X times these vectors, these 2 vectors will move, so to speak, or be transformed to these 2 vectors on the left-hand side. However, I can also say that because X is equal to these 3 matrices multiplied by each other, when I compute x times the two vectors here, what that matrix is actually doing underneath the hood is it's saying, okay, do an unrotation, and then do a scaling, and then do a third rotation. So applying these three matrices in sequence is equal to applying the original matrix to my data. So the vectors are my data, and x is my operation. And when I apply x as my operation, it moves the vectors from point A, which is on the right-hand side, to point B, which is on the left-hand side. Yeah?
Why are the arrows going in like reverse direction? Like the formula is written U, S, E, Q.
So the reason for that is just an artifact of the way we write matrix multiplication. So usually when we write matrix multiplication, we put new steps on the left-hand side. So for example, we will first do VT, and then compute sigma times whatever that matrix is, and then do U times that matrix. So we usually work from right to left when we're looking at matrix multiplications, unless specified otherwise. And so this is, it may seem weird, but you've seen examples of this before. So for example, when I write something like in pandas or in Python, right? So if I write square x, I'm applying a function to x, and then I'm going to do times 10, like times 5, for example, a square of x. And in this case, I'm applying the functions from right to left. It works, and it works in a similar way for matrix multiplication. Okay, so you've kind of seen this right to left behavior before. It works this way in code. Okay. Of course, that only works if the data is on the right-hand side. Other times the data are on the left-hand side. Okay. Okay, so what I'll do now is try to tie together SVD and PCA. The takeaway here is that SVD is basically PCA. They're almost exactly the same thing. The only difference here is that when you're trying to conduct PCA, what you'll do is you will do some manipulation to your data first. So if I go back to lecture 10 here, go to my formula. Basically, instead of taking the original matrix, original data, I will center each column and then divide the data by the number of rows. Okay. But basically, I can do SVD on D, or I can do SVD on X. But usually I won't do SVD on the matrix D. I'm going to do this manipulation and then do SVD on the matrix X here so that I can do PCA. Okay, so if I don't, I can do SVD on any matrix, but when I do SVD on this particular matrix here, it turns into the procedure that we call PCA, which is useful for dimensionality reduction. Okay. Now the most useful way to write this expression up here for SVD is via this expression right here. Okay, so these two expressions are equivalent, and this matrix here is equal to this matrix here. Okay, which means that we can interpret the terms of this equality in perhaps or hopefully meaningful way. Okay, now X here, remember, contains my original data values, and V here is an orthonormal matrix, so it's a rotation. Okay, and so what's happening here is when I do X times V is I'm saying rotate the points in X. So let me try to pull up one of my demos. Take that. And I'll load up lecture 10 too, just in case I want to pull up something from there. Lecture 10. Okay. Okay, let me skip down to, where do I have this? Okay, so I'll show you this example in lecture 9, where I had some points, and the points fall on a line. And when I compute SVD on these data here, so this right here is, I think I have 30 points. Yeah, 30 points. And when I compute SVD on these points here, the matrix V contains this vector right here in red. Okay, so the matrix V of PCA contains the direction in which I want to rotate or unrotate. Okay, so if I take this red arrow here, and if you can imagine with me, if I like rotate the screen clockwise until the red arrow lies flat along the x-axis, then what I'm doing there is an unrotation of my points. Okay, and it turns out that when I do this unrotation of my points, I find out that I don't need 2 dimensions to specify all my points. I just need 1. Right, so again, V contains this direction here, or V transpose, or like this V and V transpose contain the same thing, they're just transposed. So V here contains this red arrow, which means that if I do the inverse of V transpose, which is V, then I will unrotate my points. Okay, so multiplying X by V is the same as taking my screen here and rotating it clockwise until the red arrow lies flat on the X plane. Okay. So I have here this plot, which essentially says, originally my points had an x value and a y value. They had 2 attributes. Now, once I project my data into 1 dimension, they only have 1 attribute. Okay, so what's the difference between direction and projection? Direction says, here is a direction I want to rotate or unrotate, and projection says, here are where my points lie after I do the rotation. Okay, so the projection of this point right here, or let's say the topmost point here, the projection of this point onto my principal component is this point right here. So originally my point had coordinates, let's say this is like 19, and this right here is, let's say 27, 28. Okay, so I had x value of 19, y value of 28, but now it only has an x value of like 34. Okay, so the projection of points usually involves some dimensionality reduction, which means I need fewer numbers to describe the same point. Okay, any questions about this? Yeah.
So is one V and the other is V transpose?
So what I'm saying here is that V or V transpose both contain this vector. It's just a matter of, so if it's a column in V, then it's this vector. If it's a row in V transpose, it's also this vector. It's the same data, it's just whether or not I have it transposed. Now, the one difference here is that if I take, so originally my singular value decomposition had V transpose in it, which means when I do, which basically means if this vector is in V transpose, then it's going to move, it's going to do a rotation counterclockwise. Okay, so originally my matrix V transpose does a counterclockwise rotation, but if I say multiply by V, then it will do a clockwise rotation because V transpose and V are inverses of each other. They do the opposite operation. Okay, so if I take these points here and multiply by V transpose, I will go back to my original data. If I take these points here and multiply by V, I will rotate them and project them onto the x values here. Okay, so one relatively simple exam question is to ask you what matrix should I multiply by to do either this operation or this operation. And you should be able to say, take the first column of V to multiply to go from here to here, or take the first row of V transpose, multiply to go back from here to here. Okay. Another type of exam question I could ask is, I can give you some new points and say, what do I multiply those new points by to project them onto PCA, onto the first principal component? It's a similar type of answer. You multiply by V transpose. Okay. Now, the interpretation for the right-hand side of this expression here is not as simple. Basically, the matrix U contains the points in X in fewer dimensions. It contains like a form of the values in X, but because U has to be orthonormal, all the columns inside U need to be unit vectors. So what that means is if I look at the values in U, I don't have any code here to run, sadly. Okay, but if I were to take the points in U and plot them on the x-axis here, you would find that they have the exact same clustering pattern as the points here. It's just that they're all squeezed in so they fit between 0 and 1, more or less, because they have to be unit vectors inside of U. Okay, so U contains like the pattern of X, but it's compressed. It's like squished in so that every vector inside of U is a unit vector. So when I multiply U by sigma, what I'm doing is I'm saying, okay, stretch out the points in U so that I can get back the original magnitudes of my data. Okay, so if I plotted U here, all the points, it would be the same pattern, but they will all be squeezed into like this region on the x-axis. When I multiply U by sigma, it will stretch out the points so that they go from 0 to like 34. And that's more or less what U times sigma is doing. But it's doing the same thing as taking the original points and rotating them clockwise. So that's the connection between X times V, U times sigma. Yeah, Julie?
You have the same pattern as SV, right? Not just X.
Yes, sorry. It has the same pattern as XV. All right. Let's see, what else do I have here? Okay, so I took a long time on this interpretation. I'll go through faster these three things. So to compute PCA, let me close this here. What we do is we take our data matrix D, subtract the means of each column, divide all the numbers by 1 over square root of m, where m is the number of rows in our matrix. And then we do singular value decomposition on this matrix X. So if you take the code that I have here, skip past this, skip past here. So this right here is a code you should know. You should be able to recognize this code, and you should be able to write this code yourself. So if I say write the code to compute PCA on my matrix of whatever, you should be able to write this. And this should be like relatively turnkey. You should just know like this is how you do PCA. Okay. Let's go over the variance interpretation of PCA. Okay. So remember that PCA, when we do SVD, we don't just compute one direction, we compute many directions. What that means is the matrix V transpose contains the directions for the projection that I want to do. And that V transpose might contain many directions. Okay, so in my previous demo, I was showing you going from two-dimensional scatter plot to a one-dimensional scatter plot. But in reality, in real life, we'll go from like 30-dimensional to two-dimensional. Okay, and when we compute SVD, when we have 30 dimensions originally, then V transpose will have 30 rows, one for every direction, one for every column of X originally. Okay. Now the thing to remember here is that we don't keep all the directions, we only keep 2 of them when we do PCA for reducing to 2 dimensions. Okay, so let me run this code here so I can actually talk you through some examples. Let me just run all, hopefully that works. It's chugging along. Okay, here we go. Scatter plot, making my legislator data set. Okay, I'm going to sit here and wait for something to show up here. All right. But basically, the thing to remember here is that there are many directions in V transpose, but we keep the most important ones. Okay? And by most important directions, I mean the directions that capture the most variance in my original data set. Why do I care about the variance so much? Because the variance essentially describes the information in my data. Okay, so you can imagine with me a data set that has variance 0. A data set that has variance 0 will essentially say everyone either voted no or either have voted yes on every single bill. Okay, so that's what it means to have variance 0. There's no variation at all in the numbers. And a data set that has variance 0 has no information, so to speak, right? Because there's no way to tell apart the members of Congress because they all behave the same. Okay, so in other words, you can treat, when I say the word variance, you can substitute the word information, and most of the time, like, things will be okay. You can still make that interpretation. And so when I say variance in this case here, when I say that PCA finds the directions that maximize the captured variance, I'm also saying equivalently that PCA finds the directions that maximize the total information kept in PCA. So when I go from 30 dimensions to 2 dimensions, I'm going to lose information, but PCA tries to find the dimensions that keep as much information as possible, and the way it keeps information is by finding the directions that have the most variance. Okay. Visually, the direction with the most variance has the most spread out red points on this little black bar right here. Okay, so the red points here are the projection of points onto my principal component. And by maximizing the variance, I'm maximizing the spread of my projected values. Okay. The connection between variance and the values I found in PCA is that the values in S, let me run that. The values in S squared can be interpreted as variance captured by that principal component. So I'm going to square the values in S, and now I see, okay, my first principal component captures variance 2.33. That doesn't mean too much unless I look at the variance as a percentage of the total variance. So I can take S squared divided by the sum of S, squared, Okay? And when I do this, I find that the first principal component contains 64% of the total variance. So another easy exam question is to say, instead of taking the first 2 dimensions in PCA, I'm going to take the first 5. What's the difference between variance captured when I take the first 5 versus the first 2? And is it worth it to take the first 5 rather than the first 2? Okay. And the way you answer that question is by comparing the variance captured by the first 2 components to the first 5 components. Yeah, Sophie?
Does that mean that when S isn't squared, it's a standard deviation?
Yeah, so you can interpret S values as a standard deviation in that way too. So standard deviation is the square root of variance, and since I'm taking the squares of my S values, you can also interpret S as like the amount of standard deviation captured by every principal component, but it's not as easy to work with standard deviations as it is to work with variances, so we'll just work with variance. Yeah, Danny?
I'm still confused about what x is supposed to represent because it's not the equation for variance. Because if it was, we need or at least for standard deviation, we can square root the numerator. Can we just go over what like the x is?
You mean this x right here?
Yeah.
So this x right here is my data matrix. So this is my D matrix, which contains the votes.
Yeah.
And this is my X matrix, which contains the same votes, but I've shifted the votes around so that they're centered at 0, the origin. So you can imagine with me, if I have this data right here, let's say this data right here, one issue with PCA, or the reason why we center the data before doing PCA, is because the directions found in PCA always start at the origin. Okay, so what that means is, you can imagine with me here, if I moved all the points here up by like 10, right? So they're all the way up here now. So all the points are up here. The directions, if I do SVD on this data set directly, it will try to find a direction vector starting from 0, 0. So it'll try to start a vector here and go upward, which is not super ideal. And so by centering the data points, what I'm doing here is I want to move this cloud so that all the points are around the origin. So I'm going to take the points here and shift them down and then shift them to my left so that the center point is at the origin. Okay? And when I do that, then the directions in PCA will actually be good. Okay. Because the directions in PCA, you can interpret them as they always have to start at the origin and they always go off away from the origin. So if the points are not centered at the origin and my directions are trying to start from the origin, then I'm going to get some weird directions. Right, okay, wait, so your original question was what's X? X is the centered data matrix, and the reason why we center a data matrix is so I can interpret the directions properly. Okay, and the variance of, and you don't have to do NP square root of n in order to get the directions properly, but if you don't divide by square root of n before doing PCA, then your variances here will not be the variance of my original matrix D. Okay, so the variances described here are actually the variances of D, my original data, but I have to divide by n plus square root of m here so that the variances calculated here will match the variances in D. Does that answer your question? Do you have more questions about that?
So why just square the denominator and not the numerator?
Why do I square root the denominator and not square root the numerator? That essentially results from the calculation that So roughly, very roughly speaking, when you might remember from data 8 that when we have a sample, as the sample grows larger, the standard error of the mean goes down as square root of n. So you remember the square root law from data 8? If I pull up the textbook here, I won't go over into the entire mathematics behind why we need this, but roughly speaking, it involves, let's see here. It involves this thing right here, where variability of sample mean. Okay, so where if you take more samples, then your distribution gets narrower. And so in reality, it follows we have the square root law, where if your sample size increases by 4, then your variation within your confidence interval would decrease by a factor of 2. And so that square root of m here is more or less the PCA version of this square root law here for data 8. Yeah. So this right here is I'm not calculating anything related to standard deviation here for my matrix X. So this right here has nothing related to standard deviation, so to speak. It's just about I'm making sure that PCA does the right thing. Okay. And it just so happens that when I do SVD on this matrix X, that the sigma values here correspond directly to variance values from my original data matrix. And that's because I'm doing the square root of m here to kind of encode the fact that if I have many samples, then my expected variance will be lower. Okay, any more questions on this? Yes.
For different paths, each row is available, but why do we want column instead of row?
So the question is, why do we subtract the means of each column rather than the means of each row? And the reason why we subtract the means of each column, well, first of all, it's hard to subtract the means of each row because when you subtract the means of each row, if each column can represent a very different attribute, right? So if I have, let's see, inches of rain as one column, and I have like miles per hour in another column, and then I have like plane altitudes in the third column, then taking the average of those data values doesn't really make much sense in like a semantic way. Like it's hard to take the average of like rainfall and miles per hour. Like it doesn't have much meaning. So that's kind of like the one intuitive way of looking at it. The other way of looking at it is that in order for these points here to be centered at the origin, what I want to do is shift the points by the middle x value and the middle y value. And in the data, the x values will come in the first column, and the y values will come in the second column. So the average of the first column, if I put all these points in a matrix, the average of the first column will be the center x value, and the average of the y column will be the center y value. So if I subtract each column by its mean, then I'm shifting the points to the left, and I'm shifting the points down. All right. Yeah, question.
Can you explain like the scale of the axes?
Yeah, so the question was, can I explain the scale of the axes? That's perfect because I'm just about to get to it. Whoops, I closed the wrong lecture. So I asked a question yesterday, which was, what does the scale of the axis mean? So if this thing will load, then I have here this image, and we notice that when I do PCA on my legislator voting patterns, that the scale of the first axis here is much larger than the scale of the y-axis. So if I squint here, I can see that I have, let me just make this big. If I squint here, thank you. If I squint on the x-axis, I'm going from like negative 0.05 to positive 0.1. On the y-axis, I'm only going from like negative 0.5 to 0.05. Okay, so the x-axis is more stretched out than the y-axis. It looks like a square right now just because of the limits of my plot. But if I like make the limits like as a like 1 to 1, then you'll see that the x points are much more stretched out than the y points. Okay, and so the reason why the points on the x-axis are more stretched out is because the singular value for that principal component is larger. Okay, so let's see here. So again, you may remember from yesterday's lecture, did I ever plot the points u? I don't think so. Okay, so I had like this plot here of my projected points, and if I take, if you remember, the matrix U contains the pattern that you see here from PCA, but it squishes all the points together so that every column of U has length of 1. Okay, so if I plot, let me try to just pull this up for you. Do this, okay. Let's do that. Okay, and I think what I can do here is take votes 2D. Here's PC1, here's PC2. But what I can also do is take U1, which is just the matrix U, and U2, which is the second column of U. Okay, so if I do that, I should be able to go down here and then recreate the same plot, but instead of plotting PC1 and PC2, I can plot U1 and U2. You see the exact same pattern, right? And that's because these two plots have different limits on the x-axis and y-axis. But U, again, contains the same pattern of data after PCA. It's just that all the distances between points are not quite right. Okay. And so you can treat the magnitude of the x and y axes as a measure of how important those principal components are, because when I multiply u by sigma to get back this plot here, what's going to happen is I will stretch or squeeze in the points depending on how big the singular values are, which is another way of saying I'm going to stretch I'm going to stretch out the important directions and squeeze in the less important directions. Okay. Now, to tie it all back together, remember that our original goal in PCA was to find a linear combination of features or columns that describe the rest of our data in a good way, or in a way that captures a lot of variance. And so I showed you this plot yesterday where I plotted here the first principal component, and you can interpret the magnitudes of, so this right here is the first principal component, which is the first row of V transpose, or the first column of V. And the magnitudes here describe how every bill affects where the legislator is placed on the x-axis. So if the legislator has very positive values for this first principal component, then we're going to say they're Republican, which means that they voted no on Bill 68, no on Bill 69, yes on Bill 72, yes on Bill 74, so on and so forth, to get a large positive value. Okay. All right, well, I essentially just did the whole lecture on PCA. Like I did another lecture on PCA. It's like 10:45. Let me go over quickly. I'll go quickly what I expect you to know about text and SQL and visualization. Okay, so for text, essentially I'll ask you questions on regex. That's pretty much the way it's going to go. I might ask you some questions about string formatting, right? So if I say, like, if I give you a data set with some messy string values, you should be able to write a regex to extract out the important values of that string. We've gone over a few examples of that in class. You should be able to say, like, okay, given the regex, what strings will match the regex and which ones will not. Other like simple, like basically like gimme points that you should hopefully get on the midterm. Okay, so just be familiar with the syntax of regex. I won't ask you some crazy stuff like name capture groups or like backwards like looking or whatever. It'll mostly be, it will realistically be like simple meta characters like dots or like \d or \w or the bracket syntax, the plus operator and the star operator and the or operator and parentheses and capture groups. Okay, so roughly speaking, like you have to know, you should expect yourself to know like at least the first half of the regex lectures, the slides on regex that I had from the regex lecture. Okay, for SQL, one rule of thumb for SQL is basically everything you can do in pandas you can do in SQL at this point in time. So you should be able to take an assignment like project 1 and do most of the things in SQL, or you should at least like feel like, okay, I understand how, roughly speaking, how to do those things if you ask me to do it in SQL. Yeah, so you should know how to do slicing in SQL using where. You should know how to do inner joins and left joins and the difference between those joins. You should know how to do group by in SQL. You should know how to do case expressions and subqueries in SQL as well. All those things are fair game. Okay. In terms of visualization, so the thing about visualization is that it's kind of hard to ask some objective questions about it because oftentimes every visualization has trade-offs. So to try to ask you some objective questions about visualization, any visualization that you can do, any visualization where you can calculate things based on the visualization, you should like prepare to know. So for example, I could very easily ask you like, what is the proportion of values between 2 and 5 based on the histogram of values? I could very easily ask you, what is the height of a kernel density plot if I have a uniform kernel with some bandwidth? I went over a specific example of that in class. You should be able to know, for example, like, let's see, what types of comparisons are easier for people to make. We went over like comparing pie charts with area charts with like point charts and bar charts. those sorts of things you should be able to evaluate and decide between a better visualization. You should be able to look at a visualization and point out things you want to change in terms of the vocabulary we use in this class. So scale, right? We looked at like perception. We looked at smoothing, transformations. You should be able to take a transformed plot and go back to the original like model for the plot. So if I give you a linear regression on a transformed plot, you should be able to tell me what type of model I'm fitting to my original data and what are the parameters of that model, such as whether the model is exponential or polynomial and what constants are in that model. Okay, any questions on that? Yeah.
Just a whole question about the religion. Is it going to be pretty similar to the past midterms, and would you recommend like using those alongside?
Yeah, so it'll be very similar to past midterms in terms of there will be some programming with some short fill in the blanks, but you won't have to write like entire lines of code most likely. I haven't written the whole thing yet, so obviously I can't. I actually won't tell you even if I wrote the whole thing, but there will be multiple choice questions. There will be like some short free response questions. I won't make you write a 5-paragraph essay because that's not what this class is about. But you might have to write like a few sentences to explain your decision or explain like your answer for some certain cases. Yeah. Okay. Any last questions? Yes. Sorry? Yeah, I'm going to do it right now. I'm just going to close lecture and have you guys fill out attendance on your way out. Okay. So I did not go through the case study, but what I'll do is I'll just link John and Nero's lecture from last spring, and you can like look through the case study on your own if it's interesting to you. And so the case study in particular has some nice visualization examples or nice visualization evaluations. So I could very easily ask you like similar types of questions as the one in the case study, although I will not ask you questions about the case study itself since we didn't go over it in class. But I could very well ask you, if you go through the case study and you want some practice, I could very well ask you some of the practice questions we have in here, which are how to compute the proportion using a histogram, how to evaluate how missing values can affect your distribution here, how to interpret some strange patterns in data, like this one right here, where you have like these points that go upward in slope. Okay, so those sorts of things are just additional practice for you. You can treat it as additional practice. All right. With that being said, I think I will end lecture now and open up the attendance forms for you to fill out on your way out. If you have some more questions for me or you want to ask me about something in particular, you can come find me and I'll stick around for a few minutes to answer questions personally. Okay, thanks. And I will see you on Monday and I'll see you on Tuesday. Hope you guys prepare well. Okay, it's open. Go ahead.